Okay, so this example is from the past year final exam question. Okay, so we have to find volume of a solid bounded above the sphere and below the sphere. It looks like you have two spheres here. So first we have to sketch the spheres. Then we should know what is the solid that we should have done. Okay, so the first one, you have a sphere and it looks like your sphere is shifted at z equal to 1. So the center now is at 0, 0, 1. Okay, so the first sphere coming from the equation of x squared plus y squared plus z minus 1 squared equal to 1. It looks like to be okay, so you can directly sketch so this is 1, so x, y, z, so 0, 0, 1, so that is your center, 0, 0, 1. Okay, so that is your center, so meaning that now this becomes your new center. Okay, so now we want to sketch the okay, so this is because now z is shifted to 1 unit above, so this becomes 2 and this becomes 0 and this still becomes 1 and this one still minus 1 and this one still 1 and at the back still minus 1. So this is your circle now on z y plane. And now you're on your xy plane. Okay. So now this is on the x plane. The x plane, we have a circle now. So this is 1 and this is minus 1. Okay. And now on your xy plane, so you have this. You have this. Okay, so that is your sphere. Look for this one shifted at z equal to 1. And the other one is seems to this one, x, y, and this one z. And since now we have a regular, so the center is at 0, 0, 0, so meaning that the sketching, then we have 1 should be on the floor. So this is now 1 minus 1. This is minus 1. Yeah. This one. And this one. Okay, so this is for x squared plus y squared plus z squared equal to 1. So it looks like when we combine them together, so you have something like this. So this is at 1, and you have something like this. Okay, so this is 2, and so this is 1, and this one 0, and this is supposed to be -1. Okay, so then, and if you look at the instruction here, what is your solid looks like? Both are actually closed surfaces, but because of this said that the solid should be bounded above the sphere of the shifted sphere. So as you can see there, where is the sphere shifted 1 unit above? This one, right? That is the sphere, isn't it? Okay, above this sphere where it is shifted, the shifted sphere, and below the sphere centered at the origin. This one. Okay, so that is only the solid that we have. So the solid is bounded above the shifted sphere and below the standard sphere. Can you see that? Okay, so when the two surfaces they intersect each other, and you can have this particular shape. So maybe it will give you a circle there, right? Isn't it? I don't know the name of this particular surfaces, but it is a combination, the intersection, the combination of the two spheres. Okay, so that is the solid. Okay, so now we have to solve this. In this case, they don't mention that you have to use the spherical, but because of the solid given to you is basically from the sphere, this one sphere and this one sphere, so meaning that it's more easier for you to solve using spherical coordinate. Okay, maybe you can use the cylindrical, but the cylindrical is quite hard for you to determine the I don't think the problem with the Z. Theta also no problem. Maybe we can try, but first we want to solve using spherical coordinate, because I stated here, so this is an example for the spherical. But in exam, since they don't mention whether you have to use spherical or Cartesian or cylindrical, so you have an option. But I don't say that only spherical is applicable or only cylindrical is applicable. So you can use one of them, but maybe one of the coordinate system give you more complicated step. Okay, so now we want to solve using spherical coordinate. So to determine now you have to find the volume, right? So the formula of volume using paper. So 1 dV to get the volume. So then we want to solve using spherical, so we have to use the dV of spherical, so rho square sine phi d rho d phi d theta. Okay, about the theta. Theta is if this is your solid, so meaning that I have to erase the other surfaces. So I have to erase this. So this is not part of your and this is also not part of the solid. Okay, but we know that the highest is 1. Okay, so here then just to notify ourselves, so this one from the sphere of x squared plus y squared plus z squared equal to 1, and down here it belongs to x square plus y square plus z minus 1 square equal to 1. Okay, so now about the region. So the region is, so if you have this particular orientation, so I'm sure that you will see that, okay, in this particular orientation, so the x here, and this is y, and this one is z, so I will standing like this. So if you're standing like that, and you put yourself outside, and you're looking down, so what is the dominant region that you can see on the xy plane? So you will see, you will see maybe circle, maybe ellipse. I don't know. We can try to find out later on what explain. Okay, so how can you know that? That is the intersection between the two surfaces of the sphere. So we can find it out. So x squared plus y squared plus z squared equal to x squared plus y squared plus z minus 1 squared. So this one out. So we have the z squared equal to z minus 1 squared. So then, now we just expand. Let's see what happened next. So we have z squared plus 1 minus 2z. So z squared is gone. So we get 2z equal to 1. So z is 1 over 2. So we only, when we solve this simultaneously, the two surfaces equation, we only get z equal to 1 over 2. So meaning that this happened, the intersection happened when z value here, when the value of z is at 1 over 2. 1 over 2. Okay? But you can find out the equation, whether it is circle or ellipse, by substitute z equal to 1 over 2. Whether in this equation or in this equation, the answer will be the same. So let's say we substitute into this equation because it looks simpler, right? So when we substitute at z equal to 1 over 2, so you will get x squared plus y squared plus 1 over 4 equal to 1. So you will get x squared plus y squared equal to 1 minus 1 over 4 will give you 3 over 4. So it looks like you will get a circle with the radius is square root of 3 over 4. Because this is equation, this is the circle equation. So meaning that the region is actually, you will get a circle. Then we can use we can get the theta. If it is ellipse, so you cannot get the theta. So because your region here is a complete circle, so we don't bother about the r because we only need the theta. So the theta is 0 to pi, 2 pi. Okay, so that is for the theta, limit of theta. So now we want to look at the limit of rho and phi. Okay, so about the rho and phi, we have to look at the solid here. And as now, our solid is not the standard ice cream cone-like surface or a standard sphere, whether because of it is shifted somewhere, right? Especially for the lower cone here, sorry, the lower sphere here, where it is shifted somewhere along the z. So meaning that, so in order for you to solve the unit spherical, so it's a bit higher, which means that the function of rho or phi should be function. So and also for the rho itself, because how can you read the rho? So for you to determine the rho, so let's say I resketch the solid here into this form. Okay, this is not the hemisphere, this is not the sphere. Okay, so this is a combination of the two spheres, and I resketch here. So if you want to determine the rho, so you have to be careful here. the row here. So if you draw a line, straight line starting at the origin, so for that line, your row is 0 to, so this one from coming from the row equal to 1. So the top sphere is 1. So you can see that for the top part of the solid, your limit of row is 0 to 1. But if you look at here, it is not always equal to 1, because when this part, this is no longer located on the row or the sphere equal to 1. This one. So this one is from the equation of the shifted sphere. So in this case, in order for you to determine the row, you have to split the solid into two parts. So the first part is up here, and the other part or the other solid is for down here. Okay, I would say that it looks like if you want to solve using spherical, you have to split into two region or two solid. Okay, so the first one, when you're the first solid is the solid given by this line. So you have the ice cream cone surface. Okay, so this is for the triple integral for the solid one, where you have this particular form. Okay, you have the ice cream cone surface. So all the limit should be constant. So you have rho square sine phi d rho d phi d theta. So as you can see, as we discussed just now, our theta is 0 to 2 pi, and your rho is 0 to 1, 0 to 1. And how about your phi? So how can you know the phi? So you have to find it, because this cone, the equation of this cone is not given. So how can you know that? Okay, so you have to use the right triangular. So you know this length, right? That length is 1 over 2. And do you know this length? Yes, we know. How can you know that? So this one is 1 over 2. Okay, the length of this line is 1 over 2. And this one is from this equation. So you have x squared plus y squared equal to 3. So you have from the intersection curve between the two surfaces we give you just now, already gave you, just we have evaluate that. So x squared plus y squared equal to 3 over 4. So we know that now this is the radius of the circle, right? So we know now, evaluate the length of this, which is it is the radius of that circle. So the length of that is square root of 3 over 4. Okay, for this one, this line. So how can we know what is phi? Phi is this angle. So how can you evaluate the angle here? So you have to find the phi here, so that you can put into the limit for the phi for the solid one. So for solid one, you have to find it. So you can use the formula of maybe, since you know the length of this and the length of this, so we can use a tangent. Tangent phi is equal to the opposite. Okay, the opposite divided by the adjacent. So the adjacent is 1 over 2. Okay, so when we simplify this, so set 3 over 2 multiplied by 2 over 1. So we got this. So phi is arctangent of set 3. So then, okay, be careful when you evaluate this. So if you want to answer in the degree, so you have to set in degree. So shift tangent square root 3. So what is the answer? Okay, so it is in the first quadrant. should be no more than 90. So the possible answer is 90 degrees. So this is from the calculator. I set into degree. So I put the inverse tangent square root 3 and the answer is 60. So now we got the phi is 0 to the phi of this particular cone is 60 degree. So the limit of phi for the first solid is 0 to so what is pi over 3? Okay, pi over 3 will give you 60. Okay, so this is the solid, only the volume for the solid one. How about the rest? The rest of the solid. So you still left this one. So this part still not be calculated yet about the volume. So you have to evaluate the volume of the balance of the solid. Okay, so that is for G2. So this is, of course, this one, because you can't see the ice cream cone surface. So of course, your limit will be function. So that is quite not so direct. Okay, when we are talking about the balance of the solid, or we call that as a G2, so now we want to look at the limit of theta. So the limit of theta is still the same, because the theta, as I mentioned before, is your region on the xy plane. So we don't change that, it's still the same, 0 to 2 pi. Okay, now we look at for the phi. Okay, for the phi, because just now we said that for G1, we consider this cone, this ice cream cone surface, so 0 to 60. So meaning that for the phi, for the balanced solids, should be starting from pi over 3 to and as you can see that from that solid, where it is coming from this equation, so this one, so it looks like this one part of the phi equal to pi over 2, right? So it is so the highest angle should be 90 degrees. So you should see that the G2 here, so for the G2 you should consider this one. So now this is for your phi for G2. So your phi is, so this one is pi over 3, right? So pi over 3. So from pi over 3 now it touch the x the x-axis. So when it is touching the x-axis, so it should be 90 degree. Okay, so that is your limit of phi. Okay, now how about the limit of rho? So the limit of rho, so the limit of rho here is this. How can you determine the limit of rho? You have to draw a line starting at the origin. So now because this is, now we just sketch on the area of the G2. So you can see here your rho is still starting at the origin, which is 0, and end up along this curve. So what is the equation of this surface? So this one is the shifted sphere, right? Where the equation is given by this one. So now we are finding the upper limit. What is the equation, or what is the equation in spherical coordinate for this particular surface? So now how can we do that? So we know that this curve belongs to this equation, the shifted sphere, and then we try to transform this equation into spherical. So we have to expand so that we can have the rho squared. So from here we can have rho squared, so z squared plus 1 minus 2z equal to 1. So the 1 here cancelling out, and this one becomes rho squared. So then we have rho squared equal to 2z. Okay, so then because in spherical there is no z, you have to replace the z. What is z in spherical? So you have to substitute this equations. So rho cos phi. So we substitute z here to be rho cos phi, and then we solve for rho. And then don't forget, you cannot just directly simplify, you have to factorize. So when you do the factorization, so it is obtained that the rho 0 and the rho 2 cos phi. And as we know, the rho 0 is the origin, and meaning that the curve the equation of the curve that we are looking for here is belongs to rho cos phi. 2 cos phi. So what I want to say here now, the equation of this is given by rho equal to 2 cos phi. Okay, so now we know the upper limit is given by the equation of 2 cos phi. So now we compute the volume for so we substitute now. So this is the volume for the solid one, which is this one, and the solid given by in the green color here. Now it's become, so this is the volume one, and the second solid is given by, so you have rho square sine phi d rho d phi d theta 0 to 2 pi and phi pi over 3 to pi over 2, and then rho 0 to 2 cos phi. So you can see here your limit of the rho is not a constant, because for your green solid is not in the ice cream cone like surface, or it's not exactly a spherical. It is shifted somewhere. So now you have to find out, you have to evaluate the V1 and the V2, and at the end of that you have to total up, so you can get the total volume of the solid that you have here. So you can see here the process to get the volume of the given solid, this one, is quite complicated for spherical coordinate. Okay, so again, I don't want to do it for you, so you have to do it for yourself. I just give you the final answer. So the volume for the ice cream cone surface inside here, which is given by the G1, is pi over 3, and then for the second one, the balance of the solid in the green color here, which is G2, using this limit, and then when you evaluate that, it will give you pi over 12. Okay, so please do it yourself. Okay, I just want you to try yourself and then find the answer by yourself, and then just for practice. Okay, so here I just give you the solution, okay, the final answer. So next, what you have to do is you have to combine. So the volume of the total volume is given by the V1 and the V2, where you got just now pi over 3, and the second one pi over 12, and then so when we simplify, you will get 5 pi 12 unit cube, because this is volume. Okay, and also the answer here is given. Okay, so this is how can you use the spherical coordinate to evaluate the volume of this particular solid, where in this case you need to assume inside this there is a cone. Okay, there is a cone, ice cream cone surface, and you can evaluate this solid using the G1, and then you also need to evaluate the balance solid, the volume of the balance solid from the G2. So the total volume is given by 5 pi over 12. So the next, I will show you how can you solve this using cylindrical coordinate, and you can compare which one is more easier.